It's a pleasure to be here, and an honor, and I'm also a bit under pressure, of course, being so close to TU Delft with all these excellent colleagues presenting here the work we are doing. But I think they would agree with most of what I will say. So first, maybe a word to my person. You may not know me. So I'm now the Chair of Concrete Structures and Bridge Design at ETH Zürich. My predecessor was Peter Marty. You probably know better. I've been at ETH Zürich now for 4 years. You can see here, I think, yeah. So before that, I was running a design company in Switzerland with about 100 employees. I was in engineering practice about 15 years and came back now 4 years ago to ETH Zürich. A bit unusual in Zürich as well. I think it's similar in Delft. So I managed to do that, and I'm now in research and teaching and a bit of consulting on the side. But with this background, I think it qualifies me also to judge if the software works. And actually, I think this is quite a good tool, and I would recommend it already to my company, my former company, to get these licenses. So I will talk about these topics, so that's kind of historical background to limit analysis methods, because in the end of the day, what we do here is nothing else than an automated version, a computer-aided version of strut and tie models, which, if you're going from discontinuous struts and nodes to continuous stress fields, is very much similar, and it's based on the lower bound theorem of the theory of plasticity. That's really the basis that we have to this, what we are doing here. Then I will talk about truss models and stress field a bit more in particular. Some words about finite element calculations and other existing computer-aided tools. So why did we want to develop this additional tool? Why could IDEA convince me to participate in this? And then a bit more details on DR design, which Philip already has mentioned part of it, and I will go a bit more in detail. So to frame this, I have here a couple of examples of limit analysis methods with their ancestors, to say so. Also from other fields, like slabs here. So you probably all know the yield line method, where you formulate an upper bound of, or you get an upper bound of the ultimate load by equilibrating the work of the external loads with dissipation in the yield lines. And if you look at this, I mean, we are still using this. I teach using these slides on the right side. This has been used more than 100 years ago. Ingerslave had a very similar method. He formulated equilibrium on the rotating slab parts, and then Johansen actually established the yield line method. But you could say that's an old thing, and it's kind of equilibrium, and it's just like kind of a practitioner method to do this. It has always been there. And similar thing to the lower bound method, which is the strip method, the Rupture strip method, which is all still being used in practice, sometimes if you're not using a finite element program. And this has also already 100 years ago, the Germans had it in the coast based on works of Marcus, who distributed the load into 2 directions according to the deformations. So to achieve the same deformation at the midpoint of the slab, he distributed the loads in the X and Y direction. And Hillerborg's strip method essentially does a very similar thing. It's just that there's more freedom in redistributing the forces. But again, it's an old thing, and we could say that, yeah, it's kind of a practitioner method. We send the loads in this and that direction, and then by experience we know it works. And yeah, also in stress fields, right? So there are these very nice truss models and even stress fields in the bottom, more than 100 years ago in this case. And what we have in lecture notes and also in codes, I'll show it just after that, is very similar. So are we just doing what these guys did more than 100 years ago and just a bit doing some truss models, and it's like the practitioner knows that it will then work? Or, and what we do now directly comes from there, or is it different? And I would like to insist that it is actually different. Because it's not that it's straightforward to step from their truss models to what we're using today when we do strut and tie modeling and stress field design. So these guys, Carl Wilhelm Ritter and Emil Mörsch, who developed this, they use these models primarily to understand how it works, to explain the basic mechanisms, but they did not really design using this. So these guys in the book of Mersch and in the lecture notes of Max Ritter then, who is not the same Ritter as the one I showed before, all three professors at ETH Zürich, but we had two different Ritters. In their lecture notes, they were using admissible stress design. So these are stresses calculated using theory of elasticity, and then checking that the principal tensile stress was below an admissible threshold value. That's what they did. That was also the official way of dimensioning concrete structures in shear in this case. Right? And Pierre Largy, the successor of Max Ritter in 1951, still used this very same method. So for more than 50 years there were truss models, but they were not really recognized as something that could be really used for design. The theory of elasticity and admissible stresses were what, at least in academia, was used. I'm convinced that good designers, good engineers always made their truss models to understand the flow of forces. But it was not legitimate to show that to the proof engineer. Well, here you have these three guys again. Huh? So these models were regarded as kind of behavior models. The state of the art was admissible stress design, and that only changed in the 1960s. Why did that change? It was very similar in steel structures as well. Of course, theory of elasticity was really everywhere. And people became aware then with the time that, of course, calculating stresses based on the theory of elasticity is not the truth either. Because you have construction stages, you have restraints, in steel structures you have welding-induced stresses. So you cannot calculate the stress in a structure. And Ernst Melan here, that was a professor at TU Vienna, put that in a very pronounced way at the bottom. Actually, he said calculating stresses in a structure simply doesn't make sense. But then how would you want to design your structure based on an admissible tensile stress if you don't even know what that stress is? And that made people think. That was one thing. The other thing was, of course, in ideally plastic materials like steel structures, if they're internally or externally statically indeterminate, you have a lot of safety margin if you just end with the most external fiber of the cross-section in the most loaded section of the beam over the span, reaching the elastic limit. Of course, that's not the ultimate load. And it's very difficult to quantify then safety margins based on such a concept. And these problems were then overcome by the theory of plasticity. Established, you already have text there? Yeah. So established by Prager, Gvozdev at the same time, more or less, in the east and the west of the Iron Curtain at the time, you could say, and other people, first for ideally plastic material, they did that. They established a lower bound theorem of the theory of plasticity mainly, which many code provisions nowadays are based on, which says that if you satisfy equilibrium and statical boundary conditions, and you do not violate the yield conditions anywhere, as a designer you will provide the required strength, that's equivalent, then you have a safe design. And the ultimate load is independent of the initial stresses, as long as you have enough ductility. Now this is okay for ideally plastic, more or less materials like steel, but would you dare apply this to concrete when everyone knows that concrete is far from ideally plastic? Well, some guys did, and the pioneer on the top left side, the predecessor of my predecessor at ETH Zürich, Bruno Türlimann, he had done a postdoc and a position in Lehigh, where plasticity in steel structures was very advanced. And he came to ETH Zürich in concrete structures, and he dared to apply this theory to concrete structures. And of course, in the beginning, there was fierce opposition to that. Because, as I said, everyone knows this is not an ideally plastic material. How could that work? They did a very good job, on one hand, of course, with conceptual measures. So they designed the structure such that they would fail by yielding of the reinforcement. And this is ductile. And they provided safety margins so the concrete would not break, would not crush. And with that, you could use the theory of plasticity to design these structures. And then to overcome the criticism, what they did is large-scale testing. I have here some examples of tests. Of course, this was also done at many other universities. And with these large-scale tests, one could clearly see that these designs were actually safe if detailing was done in the right way. And in this way, they could overcome this initial opposition to using the limit analysis methods to concrete structures and increase the acceptance of them. And as a result, we have many of these in today's codes. And I forgot to say, of course, to mention, of course, these models had always been used. And for example, Jörg Schleich had been using them all the time in the Stuttgart school. But he had only could put that on a consistent basis and a mechanical background when these lower bound theorems of limit analysis became known and also applicable to concrete structures. From then on, also these methods that he had, spot and time models that initially were used for tracing the flow of forces and form finding, often based on an initial elastic calculation, so similar to what we have seen in the StatiCa, they could really be used. And these questions can be answered based on the knowledge that these methods are based on the lower bound theorem of the theory of plasticity. So this puts all of this into a mechanical framework, and it ensures that there is safe design. So having this background, in fact, you could say that these guys more than 100 years ago already did the same as we do today. Even we know a little bit better why it works. Not so much in practice, it's quite impressive, right? So if you see down here that even oops, that did not work, huh? So it moved me quite a bit ahead. I wanted to show you that here actually, but it's not working. Oh. Okay, that's demonstration effect like before. I think the laptop was slow because it was not plugged to the power. That would be my explanation. The calculation was much faster before. So this guy already had a fan here, right? If we do this, a stress field with a fanning region, you get a fan here and then a parallel band in between and another fan down there. So that was actually quite advanced, 1922. So we do similar things nowadays, indeed, but you know which and why. And many of the methods that we have in the codes, for concrete structures particularly, are based on these limit analysis methods. And it would be good if designers were aware of this, because having them in the code is one thing, knowing why is another one, and knowing that there are limitations is the third one. So these will only work if you have enough deformation capacity. So we need ductile reinforcement. You cannot put in some welded nets and expect that you reach the ultimate load. Then it's not a safe design when we design using this type of reinforcement, for example. So we have it for shear design of girders. We have it for longitudinal shear here with my nice, not so nice marks down there. We have it for torsional design. It's also stress fields. And then, of course, this nomenclature that we have here, we can use that for any D region, terms introduced by Professor Schleich, D for discontinuity. We can use for all of these, also according to the Eurocodes, truss models, or as they are called there, strut and tie models. There are code provisions for that. I can copy here some of them. Continuity regions, discontinuity regions, also in the code already. And we have design provisions for nodes, for struts, what is the concrete strength, and all of this, we have it also in the code. These are maybe not very strict stress fields, so this is not in equilibrium if I don't have here a bit of reinforcement, but it's there. So these are some slides from my lecture notes, so you can use it for any or for many different situations, and I think it's really good also for teaching. Look at this one, for example, an opening frame corner. It's pretty hard to understand, I think, why is it so difficult to do a good design, a good dimensioning of an opening frame corner like this one. So why doesn't this work? this one here. If I have all the reinforcement up here and there, and maybe I put the reinforcement with even that it looks like this, so that one down there would be. What am I doing? Okay, but that one would be like this, right? And this one like this, and it's fully anchored, you would say. Why doesn't it work? Why is it so beneficial to have this diagonal rebar here? Well, if you do a stress field analysis, you can explain that. So on the right side, you see tests, and you can clearly see that with the diagonal bar, you can reach the full bending capacity, which is here 100%. That's the bending flexural capacity of the two branches here of the frame. You can reach that, but only if you have a diagonal rebar, not in the other cases, unless you would really have an anchor plate on the outside. And why is that? Because any anchorage length and concrete cover that you have here will reduce you the internal lever arm here. This one will come down and you reduce at least the bending capacity, even if the force then goes around the corner. And this diagonal bar simply helps you to provide here length for anchorage of the reinforcement. But it's very nice that with this we can really trace the forces and explain how it works and do a design and a dimensioning and the detailing that's everything consistent. It's not then some practitioner's rules like this here implies, so put in the reinforcement this type or use that type, and you don't really understand why. You can clearly understand why one is better than the other. Okay, now you can do this with more refined models, like here with the stress fields. This was an existing bridge, cross-beam, transverse direction. You can do these stress fields even with pre-stressing if you include the anchor and deviation forces. You can combine it with graphic statics. It is very nice to do that. And yeah, you can see the flow of forces. It's transparent, gives you safe dimensioning or really an idea of how the existing structure works, if it's an existing one. You can detail consistently. Okay, everything very nice, but then this is tedious. Anything that changes and you redo the entire calculation. And already the initial geometry of your stress field, if you really go to the concrete strength and your dimensions of the compressed elements are governed by the concrete strength, that's already iterative. So it takes a lot of time. I don't know how many of you have done these types of models by hand. And if you do it and then something changes and you have to redo everything again, and then sooner or later you get to the point where you think, yeah, well, next time maybe I'm not going to do it this way. Then there is another question, which is the compressive strength of the concrete. Modern codes tell us that KC factor depends on the transverse strain. Well, here you have no idea of the transverse strain. You can simply make a gross estimate or use these factors that are in the code, 0.55, 0.8, 1.0, but you don't really know. Then, well, how about deformation capacity here? Do we have to check if we have a premature failure of a stirrup in this situation? Can we redistribute the bending moments in continuous girders enough? We cannot really check it. We have to do this with engineering judgment, and it's not always straightforward. And most importantly also, no serviceability checks. So you do these very complex and tedious stress fields, which, understand me right, I love them. I really love to do them. I think it's really great. And it's very good for the students to see how that works and everything. But then in engineering practice, under time constraints, it's just too tedious, and you end up with a result that doesn't even give you the answer to the question of the crack width and deformations. So this is why many engineers turn to finite element calculations, right? And I actually think that these truss modes and stress fields, we should put them on the list of endangered species. If we don't come up, or if we wouldn't have come up with this computer-aided tool to do them in an efficient way, they would simply disappear with time. And some academics like me would then perhaps use them to show them to the students, but in engineering practice, everyone works on their own regulations. So we needed to develop this computer-aided, and I put it even in red, finite element calculations. Looks like I don't like them. I think they're really justified for certain of course, but they have some drawbacks also. So apart from getting these very nice figures here, I took these from Athena, one of the well-known nonlinear finite element softwares. I took these because we worked with that software also to calculate our test specimens and things like that. Don't use that. So if you do these calculations first, linear elastic finite element calculations, what's wrong about that? Well, not too much actually, right? You do this stress calculation, and then I claimed before that you cannot actually know the stress because you have initial stresses which you cannot determine. But then on the other hand, if you believe in theory of plasticity, lower bound theorem, what you get from the finite element calculation is just a lower bound solution. It works. So we have equilibrium, and if we then dimension correctly, it works. It's not that bad. Certainly we don't capture the real behavior. And one major drawback that I see is that we treat reinforced concrete as an isotropic material until the very last step of dimensioning the reinforcement. So we neglect that it has 0 or 1% or 10%, if you would be progressive, of the compressive strength in tension. And we only account for that and neglect the tensile strength when we dimension the reinforcement. And that gives often inefficient and non-practical reinforcement layouts. So I think it's good for design, certainly not good for realistic capacity assessment. And in serviceability, people overestimate calculations done by these methods. And then just to illustrate, in the end of a finite element calculation, you calculate the wall, right? You have normal forces in the x and y direction, and you have the membrane shear forces. And then you can do this dimensioning as long as you make sure that the concrete does not crush. It's really that simple, right? How to put the reinforcement. And this is also based on theory of plasticity. So we turn to theory of plasticity then for dimensioning, neglecting the tensile strength of the concrete in the very last step. It's not too bad, but it's not really convincing, I think, either with this. Then what about nonlinear finite element calculations? May look like this, right? Again, taken from Athena. So you can see here that you have many factors, and you can read it. It's not too bad. So there are shear retention factors, there are fixed crack factor, there are fracture energies, many things that certainly in a design situation, it's very difficult to set these parameters. Right? Who knows the fracture energy of the concrete that we will going to be getting from the right? I usually just know the concrete strength within a certain margin. So these many parameters and also models to calculate that you have to put in make the results a bit arbitrary sometimes. But of course they are powerful tools with lots of possibilities. We use them for post-diction of our experimental results. You can account for material, geometrical nonlinearities, even buckling you could cover, of course, with these. They do capture the real behavior if you use the right parameters, let's put it this way. It's possible, but it's very tricky. It takes 2 weeks, I think, Yuri said before, sometimes even longer to my experience. And if you don't know the result beforehand, it's really a black box, and it's, if you are not experienced as a user, it's kind of shit in, shit out, if you permit to say. So you need an expert user, you have many parameters, highly sensitive to some of these parameters that you often don't really know which one to use. And last point, I think it's not unimportant. In most of these programs, tensile strength of the concrete contributes to a major or medium degree to the strength. Because to make these programs numerically stable, in many of them there are some smeared crack approaches where somewhere the tensile strength of the concrete is there. And it's hard to quantify how much of the ultimate load is attributed to that tensile strength. I've seen people recalculating bridges that have been there for 15 years or 30 years and calculated using the current codes. They don't stand. I'm sure you have many of them in the Netherlands as well. And then you run one of these calculations and it stands. It works. Okay, why is it? If I do a stress field for these, and I use 10% of the tensile strength of the concrete, I can often also prove that it stands. But we don't want to rely on the tensile strength. And in these models, depending on which material model you use, actually, there are some that are a minor influence of tensile strength, others have a higher one, and even mechanical models like the modified compression field theory, by the way, they have an average tension in there always. So that's something that I don't like too much, because our design philosophy should be, and it is, if you do conventional calculations, neglect the tensile strength of the concrete. So why should we account for it when we do a nonlinear calculation? Not so sure. Okay, is that really compliant? Some slight doubts. And for design stage, at least nowadays, maybe they will improve also, certainly they will improve. It just takes too much time. Okay, so I think they have limited use, mainly in assessment of existing structures and research. You don't have to read the white stuff here. I explained that all on the other side. Okay, so this was the point where you could, where, like Juraj also mentioned already, why don't we do something in between? So we do a simplified nonlinear calculation based on the framework of limit analysis, stress field design, neglecting the tensile strength of the concrete from the very beginning, and see where we get. Actually, this is not a new idea. My predecessor, Peter Marty, wrote in 2 papers in 1985 that it's really time now to bring these things from the drafting drawing board to the computer. Well, it took a bit longer than he anticipated, but we have now programs like that. Actually, I think it's surprising that it took that long. Of course, IDEA StatiCa Detail is not the first of these programs. There are others, some examples. So one of the very first was cast by Dan Kuchma in Illinois at the time. Now he's at Tufts University. On the left side here, very nice program, I think, actually. But he uses ACI code for doing this, which means that for each and every single strut and node, you as a user have to define the KC factor. So this node is KC1, this node is KC16, this strut is that. And then if you change geometries and these things change, it's just not very practical. And then also the user interface, as usual in these academic tools, the user interface is not really suitable for practitioners' application. Then we have this A strut and type program where we have some questions with the FC, although that's new, we have not really checked it, but it's more an academic tool. And then we have things like IDEA StatiCa for specific details, like a corbel here, which works actually very well. And the only thing here is probably that it's not general enough. It's limited to certain specific details. Lack of generality. I mean, the other ones, lack of user-friendliness. Then, one that you certainly know even better than me, stringent panel method. Developed and implemented by Professor Blauendrath and Dr. Hohenbohm. I was saying it more or less. I'm sorry, my Dutch is really limited even after the introduction. I can understand some, but my pronunciation is certainly awful. And so they developed that, and my predecessor also had a project. That works really fine. So you model the stringers as tension cords, and you model the panels using a suitable panel model, and you get very good results. The thing is, again, it lacks generality, because like in this tap-10 beam, right? Wouldn't it be nice if we could introduce here kind of like a diagonal reinforcement? I would like to, huh? And then it becomes not really that straightforward anymore to apply this method. But apart from that, I think it's a great method. Then the thing that's probably closest to what we are doing in IDEA StatiCa is the elastic plastic stress fields developed at IDEA Lausanne about 10 years ago. I was dazzled when I saw this paper on the left-hand side by Miguel Fernandez and Aurelio Muttoni, colleagues in Lausanne. So you take this example and you apply the load once on the top here, and once you apply it on the bottom. And in the upper case, the program gives you a strut action, and in the lower case, the program gives you an arch action. I have to say that in both examples, the reinforcement is defined as a reinforcement in this direction, of course, and also horizontally it's either fixed or the reinforcement, I think it's even numbers. So, but that's great, right? And it looks very similar to hand-calculated stress fields that you could draw on the right side. Now, why do we get strut action in one case and arch action in the other one? Well, actually, we do a linear elastic calculation, and all these stress fields are deformation assumptions. So they're possible, they're not deformation, sorry, that would be the finite element method, right? So if you do normal finite elements, you have deformation, possible deformations, and the program, the right solution is the softest one. In this case, we have stress assumptions, and the right solution is the stiffest one. So the one not minimizing the strain energy, but the complementary strain energy. But as long as everything is linear elastic, that's the same. Integral of sigma over epsilon or integral of epsilon over sigma turns out to be the same. And in this lower case, if the load is applied on the bottom, the vertical stirrups are very flexible compared to the concrete. So the program only wants to activate them over the length that is strictly needed, and this is enough. So even if the stirrup goes up there, it's not being activated because that would give a softer response. But the program finds that automatically. So does the StatiCa. It's just implicit in the method inside. So that helps you to find the right solution of the infinity of possibilities. Right? If you do a strut and time model, do it by hand or with the StatiCa, actually, as said already, you can choose many solutions. And actually, I tell my students, the good engineer tells the structure how it should carry the load, and not the other way around. Not the structure tells you how complex your calculation should be. You tell the structure how it should carry the loads. You can simplify, don't make your life more complicated than required. And knowing what's behind these methods, you can ensure the right detailing to ensure that you have a safe design. Actually here, very similar, and you can explain this. So that's very nice. And we also did some calculations. Jaime Mata-Falcón is in the team of StatiCa Detail. He's a postdoc in my group now. At that time, he was still in Valencia. He already used that tool from Lausanne, so he had that knowledge as well. And he got very nice results for these stacked end beams that he was calculating in this case. Now, it's not only advantages though, this program. What's really good, it maintains the advantages of hand calculations, because they really use for concrete and reinforcement, they use linear elastic, ideally elastic material. So for both the concrete and the reinforcement. With a slight hardening to make it numerically stable. But they use this, and for the concrete, of course, like this. So no tensile strength. Let's put it this way, to be consistent. So they neglect the tensile strength, and on the compression side, they have linear elastic, ideal elastic. So they don't have any tensile strength in the resistance, which is great. And they can determine the compressive strength from the strain state at each point of the structure. So you don't have to manually input KC factors. So we think that's really good, and we wanted to maintain this also in the StatiCa Detail. But it is kind of limited user friendliness. It's again an academic tool. It's limited use for serviceability, because with this stress-strain law for reinforcement, of course, you neglect tension stiffening, you get too soft responses, and you cannot really calculate any crack width with that model. It's really made for ultimate limit state. And you cannot check deformation capacity either, because this is just perfectly plastic, so if this would rupture here or here, it's not modeled. So these are the drawbacks of this existing tool. By the way, it's a freeware tool, could be used. My students have used it, and they claim it's kind of difficult to really apply it, and then you don't get the service. So I think the motivation for DR design is clear with that. What we wanted to do if you wanted to have a simple method for an efficient and code-compliant design to assess discontinuity regions. Of course, you can also calculate entire walls with it. This was starting the discontinuity region from the idea that we have these beams, and then we have the B regions, and in these B regions we have all these automated tools that directly give us the dimensioning of the beam in the B region. There's not so much of a need, but in the frame corners, for example, where we have openings, in these D regions, there we have the. But of course, the wall, you consider it a discontinuity region as a whole, as just shown by Philip, and you can also count. We wanted to include serviceability and deformation capacity verification, to have everything in one software. And we wanted to maintain the direct link to conventional reinforced concrete design. So concrete tensile strength should only contribute to the stiffness, but not to the strength. That's very important. And we only want to use standard material properties. So that's compressive strength of the concrete and the grade of the reinforcement with the ductility class, which then gives us the ductility properties that the program uses. It can be changed manually, but by standard it's B500B with 0.05 of elongation of the naked steel and 8% strain hardening. That's what's in there. And that we know in design because we ordered these materials with these specifications. Okay. It was inspired by the EPSF, I would say, and of course conventional hand-calculated stress fields. And we are using the tension cord model and the crack membrane model. I'll come back to that later. These are models developed under my predecessor. Part of it was my doctoral thesis 20 years ago. I did that. So the features is that we maintain the advantages of the truss model and stress fields. We use very simple uniaxial constitutive laws. We satisfy strain compatibility, accounting for tension stiffening, covers all verifications, and it's implemented in a user-friendly finite element-based software package. It also checks the deformation capacity. And all of this, I'm convinced we could never have done it, each of us alone, certainly not me. Because we are more on the mechanical side, of course, and not on the implementation side. And with this team, we managed to do that. And I think you can understand after what I was telling you about the limit analysis methods, these ideas, these very early ideas to implement these in computer programs, that I was kind of delighted when Lydia approached me 3 years ago if we should apply for a Eurostars grant for that. So this Eurostars grant, we have been working under this grant, partially funded, one has to say. I think each of us has invested a lot more than we get funded there, but it helped, of course. And it's going to end now, and we will keep in touch and collaborating also in the future. We're just now discussing how that will go. Okay, so maybe some more details about the model. So this is kind of a quite central part of the reinforced element, directions, horizontal and vertical direction reinforcement, with the concrete stresses in compression and tensile stresses. Now the question is, how would you calculate these? On the right side, you can see a tension cord, right here shown for the vertical reinforcement. So this is the vertical reinforcement, putting aside the horizontal direction and the shear, just under vertical tension, it would behave like shown here. So we would have here zero stresses at the cracks. So this is a crack, and then these are the concrete stresses due to the tension cord in the vertical direction. So at the crack, we have zero stress in concrete. I think you would agree, right? Because after the crack formation phase, tensile stresses transferred by aggregate interlock are really irregular. Not everyone agrees. Modified compression field theory has some tension in the cracks. I don't know how that works in the end of the day, but some people use it. Yeah? So we are strict. We say no tension at the crack faces. And that then means that if I apply a load here, I have to transfer this load across the crack. It gives me a certain steel stress. But then by bond, in between the cracks, I do get some tension in the concrete. And I do get a little reduction in the steel stresses and strains between the concrete. That's how this tension cord works. I have this tension cord in the vertical direction. I can also have a tension cord in the horizontal direction. Very much the same, of course. Now, if I want to transfer shear, if you're familiar with how that works, you have a diagonal compression field, which is equilibrated by longitudinal and vertical reinforcement. In a beam, you would have the longitudinal reinforcement in the cords, and you then bring that into equilibrium at the end of the girder somehow. In a panel, you have it distributed over the height, and the vertical reinforcement would be the stirrups in this case. And they are crossed by a diagonal compression field. Now, if I take these concrete stresses in the vertical reinforcement, and the ones that I get in the horizontal reinforcement, again with the crack spacing, and now I assume that I don't have vertical and horizontal cracks, but I have one set of diagonal cracks, as I would get for dominant shear. I don't get this set of cracks and that one and some shear, but I get one set of inclined cracks in the web. Then I can assume a diagonal stress field aligned with these cracks, uniform stress field, and superimpose these concrete stresses in the tension cords to these concrete stresses. And then I get the stresses that you can see here. So that's compression and tension stresses in the concrete. So these stresses here, the compressive stresses are in this direction, and the tensile stresses are perpendicular to the cracks. And you can see that because both reinforcements have zero stress at the crack, of course also this crack will have zero stresses at the crack, but in between the crack I get some tension in the concrete, and now also my concrete compressive stresses between the cracks are a bit lower. This is an important point when I come back to the compression softening relationships. So at the crack we have a higher compressive stress than in the middle between the crack. For non-isotropic reinforcement, the principal directions will also rotate slightly between the crack. So that's not entirely 100% consistent, but maybe 99.9. We have done these calculations, it's very little. Because bond stresses are not the same in two directions, cracks are flatter than 45 degrees, and then one direction gets more temperature stiffening than the other. Okay, so we assume these fictitious cracks stress-free. That means that principal stress and strain directions coincide. That's this orange ellipse. We have zero tensile stresses at the cracks. So maybe I should clear what I've been drawing, because now it shows up in the animation. And you won't be able to tell what's my drawing and what's the animation. Okay, yeah, that's also very important. Of course, in the end of the day, we're interested to formulate equilibrium in terms of the stresses at the cracks, maximum steel stresses, zero in the concrete, to not have the tensile strength of the concrete in the resistance. But then for the overall behavior, we're interested in the average strains. The local strains at the crack are unimportant. We're interested in the average strains. So what we need in the end of the day is a relationship between these average strains and stresses at the cracks. Equilibrium at the cracks, and we have the maximum stresses at the cracks, and in between they're a bit lower, and the concrete tensile strength does not contribute to the resistance. But it does contribute to the tension stiffening, because now if I take a crack element here, and I calculate this elongation, what is it? It's the average strain, or the integral of the steel strains over the length divided by the original length. That's the average steel strain, and not the maximum one at the cracks. So this is how I get a stiffer behavior, which helps in reducing crack widths. Okay, then here again, you can see that also. And this assumes minimum reinforcement. I will show that on the next. Then, for the concrete, we use very simple, based on the codes, parabolic and then constant, with an ultimate strain, and we reduce that by the famous Kc factor. Now, as said, we have in the codes, we have these factors, in axial compression 1.0, if it's orthogonally crossed by reinforcement 0.8, in a diagonal situation 0.55. Of course, we can't use that, otherwise no one will want to use the program if you have to tell in each finite element what factor you should use. So we rely on these relationships that are compression softening relationship, already mentioned by Philip as well. There you have the principal tensile strain. So allow me to go back here quickly. So this is the strain in this direction here, perpendicular to the compressive stress field. And we know that from the calculation and the KC factor. Now in literature, you'll find two different curves for this. You find one for the modified compression field theory, which is the solid one. And we have one, which is the dashed one, which is in the FIV model code. And there's a significant difference between these at higher strains. And we are using the upper one, the red one, the model code. Why? Because we are checking the stresses at the cracks where they are higher. Modified compression field theory is formulated in terms of average stresses between the cracks, and there the stresses are lower, so checking their experiments, fitting them to these curves also gives them a lower value. Besides, many of these points down there, to my check that we've done, they are stirrup failures. They're not even concrete crushing failures. So we use this upper curve, which is in the FIB model code 2010, and we adjusted it to get for uniaxial compression a value of 1.0, so to make it compliant with the Eurocodes. And actually what we're doing here is permitted by Eurocode. So it says you have to use these KC factors that they give, the specific ones, unless you use a more rigorous approach. And that's what we're doing. These curves have been calibrated on tons of experiments and proven to work. Okay, so this is the curve that we are using here for the compressions. Then we need a model for bond in terms of anchorage. What I've showed before, that tension cord, implicitly I assumed that we have a constant force along that tension cord. So no problem of anchorage of the rebars, symmetric situation in each crack element. Of course, at the end of the rebars, or if we have gradients in the forces in the rebars, we don't have that situation, and we have to check this code compliant using a similar approach as for the anchorage length that we have in the codes. And there what we did, we back calculated the bond stress that corresponds to the anchorage length in the codes, and we are using this as a constant value for anchorage problems along the rebars, if you have a gradient in the tension cord force. And in between, to model the tension stiffening, we use such curves that relate now the average strain to the maximum stress at the cracks, index R. Sigma is R. R is at the crack. So what you can see here is that tension stiffening reduces the strain, makes the behavior stiffer. At failure, it reduces deformation capacity quite enormously. Even for a B500P, it's amazing how much reduction. But it does not affect the strength. We keep the same ultimate strength. We only make it stiffer. And that's with the tension cord model that I've showed. Explain this one. So the tension cord model that we are using relates the average strains over the crack element to the stress at the crack. Now you could do that using bond stress slip relationships like this one, right? As you will find in an FIB model code or in other places. We are using here the formulation of the tension cord model, which simply assumes a constant stress before yielding of the rebar and half of that after yielding of the rebar. You have to be aware that this bond stress, a constant bond stress along a nominal perimeter of a rebar, is a very drastic simplification by itself. It works completely different. The ribs are transferring the forces by local compression and so on. Many people have investigated that. And then the question is, should we really, if we're in the end of the day interested in the integral behavior of average strain versus force, do we really have to care about if this curve looks like this or if it looks like this? If we can simulate this with this very simple model that captures the main effect, which is more or less a constant stress, which can be calibrated. It's about twice the tensile strength of the concrete before yielding, and then it drops after yielding of the reinforcement. It's not dropping because the rebar contracts at yielding, as some of my colleagues ultimately have written. It's so little contraction at that moment, but the strains at the moment and the slip with that, the steel strength and the slip increase dramatically once the rebar yields. So we have tenths of a millimeter before it yields, and you go into millimeters and more once the rebar yields. So this curve actually doesn't look like this, but it looks like it's this transition area virtually doesn't exist. Then it's not so important to really capture that exactly. The important thing is to have a reliable and closed form relationship between average strain and maximum stress at the crack to make the program also computationally efficient. If you want to solve that second order differential equation of bond each time for each rebar, you would wait a little bit longer than we were waiting before. So with that, you can do that, and you can calculate all of this. It's based on works done by my predecessor, Manuel Alvarez, who particularly had his thesis dedicated to this. And actually, even in Eurocode, if you look at these formulations, they actually do assume a constant bond stress as well. So it's also non-applying to these. Now this works for minimum reinforcement, at least, or more. So the rebar does not fail when the crack appears. If I'm below that with the reinforcement, and I'm quite often, because the stirrups have minimum 0.2% of reinforcement. If you would do a tensile test in the direction of a stirrup, it would always rupture, because it's much below minimum reinforcement. But we know it doesn't, because the cracks are controlled by other parts of the structure, the chords in a web, for example. Now in this situation, if we're below minimum reinforcement, we need some way to average the strains that we get from the program over a certain length. And here we simply use, we go through the animation, we simply use as an averaging length the length that we would need to fully anchor that rebar in the concrete. Actually, with such low reinforcement degrees, what you get is kind of a pull-out situation of the rebar out of the concrete to the left and the right of the crack. Actually, it's not pulled out, it's fully anchored. It will start yielding, and then it will rupture at a certain strain when it has reached its ultimate capacity, and it will activate concrete until this length that's required. To calculate that one was an equation chord model and use this length for averaging. It's particularly important for stirrups to check stirrup temperatures. Okay, so now then this gives us these stress-strain relationships of the reinforcement. Average strain versus stress at the crack always. And you can see here for 4% of reinforcement, compared to the white line, which is the naked reinforcement, we get a drastic reduction of deformation capacity. We also get a stiffer behavior initially, which is here. So here we go to epsilon of yield, which is this one here. So this is scale on the horizontal axis, also a bit on the vertical axis, not so much. And for this stirrup pull-out situation, we use this curve, and in the other cases we have these curves here. And we neglect the initial uncracked behavior. We can activate that for more refined calculation, but it's not recommended usually, because you might always have an initial crack from shrinkage, from other effects, and so on. So in the standard version, it's not that common. Now, if you look at this graph here, these three blue curves are the response of the same rebar with a different reinforcement ratio. And there's quite a difference. And the magic number here is the reinforcement ratio. It depends heavily on the reinforcement ratio. Now, do we know the reinforcement ratio? Well, that's a tricky one. How do we determine the reinforcement ratio so that it works and define it in a way that it works in all situations? Any discontinuity region you may come up in the future, it should work. That's not straightforward. And there also we had to do some compromise, getting a bit away from the mechanically strict, consistent models to something that's also usable in the day. Let me explain briefly how we do it. So in the first step for each rebar, we determine the concrete area that this rebar could activate if the concrete works at its tensile strength. So that's the reinforcement ratio where the rebar would be fully anchored to its ultimate strength, rupture, not root strength. And that's always about 15 diameters for a B500 in this case. Then we apply a cover symmetry conditions, drawn here for rebar 3 and 4. So this is the simpler one. There it's simply, if it's outside the section, of course, we have to neglect it. We don't have that concrete. And then we also neglect it on the inside of the section. Now for this rebar down there, we do the same. We neglect this part because this part is out of the cross-section. But we do take into account that green one. Because of course, symmetry condition, we have another rebar over there. Now actually checking if there's a really symmetric rebar on the other side is not that straightforward. And in the end of the day, we account for this if it's covered by more than 50% by other rebars. But the condition, it works really pretty well. But that's maybe the kind of adjustment we have to make it really generally applicable without asking you as a user to specify the reinforcement ratio for each rebar. So in codes, I know that some just take twice the concrete cover, others have mechanical formulations for bending, but we don't know beforehand if this will be bending, tension, or whatever. So we have to come up with a reasonable solution. And then we take this concrete area and we attribute it to the individual rebars. Now looking at the test here by René Walter, carried out in Stuttgart. So if you look at this tension cord, probably was the format of the slide, so this one here should be down here with the cracks being shown here. You have to turn it around. So the steel stresses and then also the steel strain will be highest at the cracks. So these are the cracks here. Get the highest stress and also the highest strain there, and in between it's a bit less. So how do I calculate the crack width? From the strains that I get from the program. It's important, the program does not assume specific real cracks at a certain location. It assumes that the crack might be everywhere, uses that stiffness, but where the crack then will appear is not defined. So we have a continuous distribution of the strains resulting from the program, and we have to determine the crack width. So what we do simply is we calculate the crack spacing using the tension cord model, and then we calculate the crack width by subtracting the concrete strains between the cracks from the total strains integrated over the length. And that works pretty well. What I have to say, of course, this is not an exact science. This is also sometimes I saw before like 3 digits of significant digits of the crack width, 0.237 millimeters. We have to be aware that we have uncertainties in cracking. And one of them is a very heavy one that we cannot overcome. If you take a tension cord, load it in tension, and make it crack, you can determine the crack spacing theoretically by no more exactness than a factor of 2. Because you may get the crack spacing, and then you have the tensile strength of the concrete just reached in between 2 cracks. And the new crack may form or not. That's a factor of 2. And we always have this uncertainty, and we can improve the program as much as we like. We will not get around that. And they can make the formulas in the codes longer and longer, and they will not improve that. There's an uncertainty in this. And here we use the expected value of the crack spacing, which is 2/3 of the maximum crack spacing, which gives also safe values for the crack openings. Okay, so this is for a stabilized crack pattern down there. So this is a deep beam, it's simply supported here, and then it has a lot of reinforcement down there, and it has some very light reinforcement up here. What happens up there, where we don't have a stabilized crack pattern? We again have the problem that now from the strains that I told you before, how we estimate the stiffness, we have to calculate the crack spacing. The crack, not the crack spacing, but the crack opening. And we have a similar situation in such situations where you have a re-entering corner, like in this end beam, and this crack appears very early in the loading process, and we don't get the chance to get more cracks in serviceability. They will appear, but only in your ultimate load, and we're interested in serviceability. So we have one single localized crack, similar as in the web when we are below minimum reinforcement, and cracks are controlled by other reinforcement. And in these situations, we get from the program a strain distribution like this one shown on the right here. So this strain distribution here. Yeah. And we have to calculate the crack spacing. No, because we don't have crack spacing, we just have one single crack. But we have to calculate the crack width. How do we do it? We do this. Now you say that's unconservative. You're not integrating all the strains, right? But for example, in this situation where you have a lot of reinforcement here and there, you would actually get, this is the crack, huh? You would get the next crack here, the next crack here, the next crack there, and the next crack there. So this one here, if that's this crack, and the next one is this crack, it would look like this actually. And we would only have to integrate from here to here. So this would be the crack width. What we're doing is we're integrating over the entire length that this rebar will be activated if it's pulled out, even if we're above minimum reinforcement on this situation. And that gives us higher values for the crack opening. It's important because we always got two small crack openings in these tapped end beams, and we did not want to provide you with unsafe results. So this was our explanation, that we have one localized crack, and we have to activate the rebar over the larger length than the theoretical crack spacing, because these cracks have not appeared yet in this image. Okay. So in this situation, I think that's for version 9.1, though I'm not quite sure, but it's probably not in the actual. Okay, then, well, a detail on how do we calculate crack openings. A crack, say, this is the crack opening, orthogonal to the crack. We calculated along the rebar, so this is what we get from tension cord, if we treat each reinforcement as a tension cord. And then, of course, we have to transfer that, and actually, the crack opening is a bit larger than the crack displacement aligned with the rebar. So we get this, it's the value that I showed before, and actually the crack opening is 1 over cosine times bigger. Okay, some experimental validation. Maybe not too much to save a bit of time. I am at 1 hour now, so I would have 15 minutes, but I think coffee is also a good idea. So I go a bit fast here. I have 4 series of experiments. One are direct tension experiments by Manuel Alvarez at ETH Zürich. These were elements, they were the basis of the tension cord model. So this is 3 meters. These are really large specimens that we tested. You can see here 4 of these all have the same reinforcement, except that here I have a lower reinforcement ratio than in the others. Here I have not so ductile reinforcement, and here I have a high strength concrete. This one does not have a large impact. This one is really a problem, and this one is more or less as expected. Show you. So if we do the calculations, we can see that we get these results in the experiment. So we get almost the same load for these 3, and of course less, where we have less reinforcement. Would be really bad if we weren't able to calculate this, right? So the tension in the crack is transferred by the reinforcement alone. We know the material properties. We need to get close, and in fact, we are very close with the results. But then, what's more difficult, we also get very good estimates or calculations of the deformation capacity. So the reinforcement here, let me go one back. I think we have the number there. No, it's not there, but it's one of the next slides. So the ultimate strain here was 7%, 4.6% calculated. and in the test it was almost 7% in both. Here it was 40% calculated, 0.4% for millistrains only, with the low ductile reinforcement, so that's a factor of 10 less. And here in the experiment we were also pretty close, and the same for experiment number 8. So here we're pretty good in the ultimate load, and we're reasonably safe with deformation capacity. If you look at this, these are the low deformation behaviors, and you can see here this dramatic reduction of deformation capacity. It's dramatic in all of them, but in terms of the percentage, it's much more pronounced with the low reinforcement, low ductile reinforcement, which actually at the time was termed normal ductile. So these here, the other ones nowadays would be a B500B, and this is B500A, more or less according to the current Euro codes. Then in these same tests, we also checked the crack width. On the vertical axis here, and on the abscissa we have the elongation. Again, set 4 has a scale factor of 10 because it's much less ductile. And you can see that our crack width predictions, the solid line is what you would get with the standard parameters from the program, and the orange points and lines are the results. I think that's fair. What would we get here as results? We're actually pretty happy to getting this. Okay, next series from St. Prien, 1980. They did bending tests on elements with this cross section with a lot of reinforcement up there, a little bit here, and none down there. Got this crack pattern, but I think that's quite a tricky one to predict the crack widths. So we did that without any cheating, I must say, because it's always easy if you can adjust many parameters, but maybe you look at this one, which is the standard parameter of ideal. And of course, it's not perfect in this region here, but that's also the most difficult one. But I think it's pretty good overall. What we get here. This is the crack width over the height. Clearly, you can see that the heavy reinforcement up here, although it is gets the highest load, it restrains the crack opening, and these here are simply not capable of restraining it. So the cracks open more, although the strain is less. What from St. Prien here wanted to show, by the way, with this experiment, so you can reproduce that. Then here we have 3 shear walls. 2 of them were about 3 meters high. The one was 4 meters 50 high. 1 meter 50 here, 1 meter 50. Vertical load constant, about 1.4 meganewtons. And this had a bit less vertical reinforcement. Transverse, they were all the same. And yeah, that's it. And then we recalculated these also. Yeah, maybe here you can see that this was high ductile reinforcement, because they did not want stirrup ruptures in these tests. And what we get here is failure loads are really well predicted. And of course, these were cyclic tests, and we wanted to fit the backbone, so the highest shear resistance up to there, how the curves are going. Failure was by torsion of the concrete in compression, looked like this. This was the experiment, and this was the calculation. So we end a little prematurely. We also have comparison without tension stiffening, but I think it's pretty good prediction, because in this range here, what's really going on, it starts softening. That's very difficult to model. These are the standard parameters that we were using. And then the same for the 3 others, the 2 others. I think that's pretty good, also in terms of initial stiffness, although that's neglecting the tensat, the uncracked behavior, and it has a strict strain limitation on the concrete. If we use a refined set of parameters, we would get these curves. So if we cheat a bit in terms of adjusting this and that parameter, as we usually do when you do these nonlinear finite element calculations, even with this program, we get really close to the real observed behavior. Won't do that in design. For design, this is fair. Okay, and you have these plots that Philip has already showed you. And maybe the last one, these are tests in shear. And maybe just, well, these are 1 meter or half a meter deep. Recent tests in Vienna. at Professor Kollecker's chair. With different layouts of the reinforcement. They did these tests. And you can see here, this is not so ductile stirrup reinforcement. All these failed by rupture of the stirrups. If we calculate them, we get pretty close with DRD. So this is the white lines. And it looks odd here, but this is the experiment versus the calculation. So if it's smaller than 1, it's unsafe. We did the calculation neglecting tension stiffening, and we can see that we get unsafe results because we are not capturing the stirrup rupture there. Because in NVIDIA, we calculate and we get this stirrup rupture, also the right failure mode that is governing. And neglecting tension stiffening may be unsafe because we are not checking the deformation capacity for this type of reinforcement. We did this comparison also to convince our colleagues in Lausanne that it's a good thing to account for tension stiffening also in terms of structural safety, not only for serviceability. We really need to take that into account. And it's more pronounced for high beams, which are more close to what we are building in reality. So that's a little bit of a concern. It was also made because we have many engineers in Switzerland that use extremely flat inclinations of the stress fields to assess existing bridges. And that's exactly where you get these problems with the stirrup ruptures. And then you have these very thin stirrups with extremely good bond conditions, and they tend to rupture. And I'm a bit afraid that there sometimes we maybe not on the safe side. That's why we also did these calculations. And Cooper-Kollecker's tests show that it's really an issue. Okay, so if you run it without tension stiffening, which would be the PSF as they do in Lausanne, or you do it with the tension stiffening, in the upper case you get the right failure mode. You get a KC factor of 0.64, and the concrete is only used to 42%, but the stirrups rupture. If you neglect tension stiffening, the program will tell you that it fails in compression down here because the KC factor is really much lower and the concrete is reaching its definite limit. So you're not capturing the right failure mode there. And that's what's also on this slide here. Yeah, so if you go to that one on the right side, you can see that if you're not taking into account tension stiffening, then you're not capturing the right failure mode. So here, without tension stiffening, this is how much is the concrete used in compression. It's always 1 if we don't account for tension stiffening, because we are not activating that rupture strain limit of the stirrups. We can always go flatter and flatter and flatter, and they will yield, and they will get several % of elongation, but they would have ruptured much before, which we capture with ERD. Where at ultimate, the concrete is quite relaxed at about 50% of its capacity, but we can see here, no, it's not on that one, it is on the other one, that it's the stirrups are actually rupturing. And have it on the next one also? No, there's no option. Okay, so this is also good tension stiffening, not only for serviceability, but also for